Hello everyone! Like and subscribe to my channel.
Amino acids serve dual roles, fueling either building up or breaking down processes in your body. Let's first explore anabolism, which is essentially the body's construction phase for creating new, vital tissues. During anabolism, amino acids are the fundamental building blocks for synthesizing all sorts of new proteins. These new proteins can be structural, like the muscle fibers actin and myosin, or fibrous, such as collagen for connective tissue. They also form critical functional molecules like hormones, necessary enzymes, or specialized transport proteins in your bloodstream. Antibody proteins, known as immunoglobulins, are another crucial type built from this process. The entire construction sequence is precisely dictated by your DNA, starting with the primary structure. Remember, the primary sequence is simply a specific string of amino acids held together by peptide bonds. If a required essential amino acid is missing from this chain, the protein cannot be fully created. However, if a non-essential amino acid is missing, the body can often compensate through a process called transamination. Transamination involves transferring the nitrogen or amino group from one amino acid to another compound to make a needed non-essential one. Once the primary sequence is complete, the chain then coils and folds into complex secondary, tertiary, and quaternary structures until it becomes fully functional. Shifting gears, we move to catabolism, where amino acids are broken down, sometimes specifically for energy production. In the liver, the first major step is deamination, which is simply the removal of the amino or nitrogen group from the carbon skeleton. This detached nitrogen is then converted into urea through a dedicated process called the urea cycle. Once formed, the urea travels from the liver to the kidneys to be safely excreted from the body in urine. The remaining carbon skeleton can be transformed into glucose or ketones to be metabolized for immediate energy. Alternatively, these skeletons can be diverted for the synthesis of cholesterol or fatty acids. While all skeletons can yield energy, only glucogenic amino acids can ultimately form glucose, and only ketogenic ones can produce ketones. A special case is branched-chain amino acids, which are metabolized directly within the muscle tissue itself. Since the urea cycle only happens in the liver, the muscle needs a way to shuttle that nitrogen over, which it does via the glucose-alanine cycle. In the muscle, a branched-chain amino acid is first transaminated, giving up its nitrogen group. The resulting carbon skeleton is used for local energy, glucose, or fat, and the nitrogen is transferred to make the non-essential amino acid alanine. This newly made alanine then travels from the muscle to the liver, where it is demented into pyruvate and the nitrogen waste. The nitrogen waste enters the urea cycle, and the pyruvate is available to enter the process of gluconeogenesis. Essentially, this entire cycle cleverly transfers the metabolic burden of making new glucose away from the muscle and onto the liver. Unlike carbohydrates and fats, your body has no dedicated storage depot for protein that it can tap into later. This lack of storage necessitates continuous recycling of amino acids through the constant removal and addition of nitrogen to maintain balance. In a perfectly healthy state, the amount of protein you ingest is precisely matched by the amount you excrete through various means, which we call nitrogen balance. Your muscle tissues are constantly undergoing both breakdown and resynthesis, drawing from that central amino acid pool. Negative protein balance occurs when the body breaks down more protein than it is currently consuming, which is a catabolic state. This breakdown state usually happens during periods of high physiological stress, like severe infections or major trauma. Conversely, positive protein balance means the protein you consume is greater than the protein you break down, occurring during growth periods like childhood or recovery. Resistance training that overloads the muscle to promote synthesis is another situation where a positive balance is typically observed. Importantly, simply eating a very high protein diet doesn't automatically guarantee muscle growth or a positive nitrogen balance. For instance, an endurance athlete eating lots of protein but not enough carbohydrates for their activity will rely heavily on muscle for fuel. Consequently, more protein might be catabolized than consumed, leading to decreased performance and worsened strength due to that protein breakdown.